Starting with a resting neuron, it starts out with a charge of minus 70 millivolts. Sodium starts on the outside of the cell while potassium begins on the inside, while potassium also has a higher membrane permeability than sodium does. The second step is depolarization. During depolarization, neurotransmitters get released from the presynaptic cell and bind to the receptors located on the postsynaptic cell. Once they bind in a chemically gated channel, sodium increases and pushes into the cell. This large increase of sodium causes voltage-gated channels to open up along the rest of the axon, creating a more positive charge. As sodium is rushing into the cell, the ICF increases in charge, pushing the stimulus beyond the threshold and carrying us into our next step. The next step is repolarization. Due to the abundance of positive charges inside the cell, potassium channels begin to open so potassium can start moving out to the ECF. This causes the charges to become negative once again, restoring them to their previous state. Step 4 is hyperpolarization. During this step, even more potassium leaves the cell, bringing the charge even lower than the original resting state of minus 70 millivolts. And for the final step to bring everything back to normal, the sodium-potassium pump begins pumping potassium back into the cell and sodium back out. Bringing it all together, starting at rest, a stimulus occurs, causing sodium to flow into the cell, increasing the charge known as depolarization. After reaching 40 millivolts, potassium will begin to re-enter the cell, known as repolarization, and as more potassium leaves the cell, we will reach hyperpolarization, dropping the charge below minus 70 millivolts, finishing with the sodium-potassium pump to kick in and bring everything back to normal.
The action potential arrives at the end of the motor neuron, and acetylcholine is released. Acetylcholine binds to receptors on motor end plates. Sodium then rushes into the muscle fibers. The muscle action potential travels up the T-tubules. The sarcoplasmic reticulum releases calcium. The calcium then binds to troponin, which causes tropomyosin to shift and expose the myosin binding site. Myosin binds to actin. Myosin pivots, pulling the actin filaments. Myosin then releases from actin, and myosin re-extends into the ready position.
In the first step of muscle relaxation, nerve impulses stop. During the second step, stimulus to the fibers ceases. During the third step, acetylcholine esterase decomposes acetylcholine. Next, the calcium ions return to the sarcoplasmic reticulum through active transport. Finally, cross bridges break, actin and myosin slide apart, and thus you have muscle relaxation.